Almost time to get started. Any questions pop up? Is the sapling homework system working okay? Guessing if it was, you'd say something. I wanted to actually start today by playing a very short video, and this is the astronomy picture of the day today, which was the big news yesterday, and it's I'll pause it here. It's the, what did they name it? The Ingenuity helicopter, Mars helicopter in flight. And so, all right, now I've got crud in the way down here. I must have a notification or something. Okay, it's this little thing right down here. And they just started the motors on it. It's not a very long flight, but they just wanted to know if it would work. Pretty much it just went more or less straight up and came straight back down and landed. The problem is that the way that a helicopter works is when you spin the rotors on it, I'll pause that. When you spin the rotors on something like that, that's what the rotors push down on the air. And we're going to study Newton's laws here, well, after the first test. But then if the rotors push down on the air pushes up on the rotors, and that's what lifts the helicopter. But on Mars, the air is about 0.6% as dense as the air on Earth, 6/1000ths the density of the air on the Earth, and so there's hardly any air to push down on. And so this little tiny helicopter had great big long rotors on it, and they spin really fast. They have two rotors spinning in opposite directions actually on the thing, and that's the challenge. And they didn't know for sure. They calculated hoping it would work, and it did appear to work okay. It hardly weighs anything. I think on Earth, I can't remember how many pounds it weighed on Earth, but it wasn't very much. Because you have so little lift on Mars, it would be difficult to actually get a much of a payload on the thing. So it'd be hard to have very many instruments on it. But maybe they could get some kind of a decent camera on it and take a lot of pictures at various places. So, but it has to have a battery on it too to run those rotors. So anyway, that was the big news from Mars this week. I'm going to switch over to my IPEVO screen here, and we'll start with some questions that are just sort of thought questions. And this is out of a book that was written by one of my professors when I was a student at Eastern. He wrote this whole book that had nothing but this sort of questions in it, and things to just get you thinking about some of these ideas. And I used to have my students buy the book, and they'd have a couple of these that they had to answer, usually for every day's class, and they would call them Gibbs questions. The professor's name was Bob Gibbs, and unfortunately the book went out of print, and I still have a copy somewhere but I just photocopied them now. But anyway, here's the situation. We have a ball projected upward from ground level as shown in the figure. And so here's the ball when it's just before it's launched, and it's shot upward here. We assume it starts at x equals 0 and that the upward direction is positive. So that's what we've been doing on our free fall problems so far. So we've been using that idea. And in the table of figure 2.22-27b, which is this little table here, fill in the boxes with the proper sign, plus, minus, or 0 of the quantities given, and explain each response. So, on the way up, is x positive, negative, or 0? I'm guessing since x is 0 here and positive is upward, as soon as it leaves the ground, its value is positive. So that should be positive on the way up. What about the velocity? Well, velocity has direction. If it's moving in the positive direction, velocity is positive. And so velocity on the way up, it points up. And so that's positive as well. Acceleration, well, this is a free fall situation. We've been talking about this. The acceleration is negative if up is the positive direction. And so this gets a minus sign. When you have a positive velocity and the acceleration is negative, that means that the thing is being slowed down. And so, yeah, on the way up, the ball slows down. All right, well, what about at the top? Is the position positive? Well, is it above the floor or the ground? Yeah, it's still above the ground, so x is positive. What about the velocity at the top? Well, that's where it stops and reverses direction. So the velocity at that instant is 0. What about the acceleration? Okay. This one's a little bit tricky. A favorite answer of people is to say the acceleration must be 0. But if the acceleration is 0, it's going to stop there and it won't come back. And here's a way that will help you deal with the acceleration. Acceleration is the change in velocity divided by the change in time. And we have to consider it for some time interval. We can't do it at some instant and just say that's what it is. So we'd have to think of the velocity, maybe, oh man, seasonal allergies are getting me today, but you'd have to imagine some instant before it's at the top, an instant after it's at the top, but at any rate, you still end up with that very same negative acceleration when it's at the top. Okay, on the way down, well, if it hasn't reached the ground yet, the x value is still positive. Okay, the velocity on the way down, it's now going in this direction. That's going to be negative. And the acceleration is negative also. Now, you've got negative velocity and negative acceleration. They're both in the same direction. That means it's going to be speeding up on the way down. And yeah, that happens. Its velocity was 0 at the top, and it increases the velocity, or the speed increases steadily on the way down, but it's a negative velocity that's getting larger in magnitude on the way down. So if you're watching the video of this, you might back this up and think your way through each of these things and do that. There was a problem right after this, and when I copied these, I didn't copy the problem numbers, but this refers to the same situation. So the ball projected upward, X is positive upward, and so forth. In the table of figure 228, which is what this one is, indicate in each box if the variable is increasing, I, that's what we'll use for increasing, decreasing, D, or not changing. And then explain each response. Well, I'll explain them vertically. But if it's on the way up and X is 0 at the bottom, then X is going to be increasing on the way up. They're using the vertical direction as X. We were using Y yesterday, but this would be increasing. Okay, at the top, well, at the top for that instant, the X value, the height, will not be changing. So I can put an in there. On the way down, the X value is upward, but it's decreasing and it hasn't reached the 0 level for X yet. So the X value is decreasing on the way down. Okay. Well, what about the velocity? On the way up, well, just imagine holding a ball in your hand and throwing it up as high as you can, straight up if you can. It's going fastest at the instant it leaves your hand, but then it slows down steadily on the way up. And so the velocity is actually decreasing on the way up. Let's see. At the top, the velocity is, well, what does it mean to be stopped for the velocity? At that instant, it's not fair to say it's not changing, but at that instant, you might be able to say that. Or would it be better to think of something else? Actually, let's write our velocity equation. Okay, this is what we were using yesterday for figuring out the velocity for, this is for our free fall problems. And we were assuming up was positive like we are for this problem. You actually might be able to say, if by decreasing you mean moving to the left on a number line. So if I made a graph of velocity versus time for this thing, and it starts off at V naught. So here's V as a function of t, and what this graph will do is head down like this. Okay, now starts off with a positive velocity. The magnitude of the velocity decreases steadily. Right here, that's when it's at the top. Okay. And then it steadily goes toward the negative direction. If we want to call that decreasing, we can do it all the way through here. The slope of this graph is the acceleration. That's constant. And we have a steadily decreasing velocity. If you're talking about speed, you have an increasing speed here. That's just the magnitude of the velocity, but the velocity itself is a decreasing number, becoming more and more negative. And so you have to be a little careful what you're talking about. This acceleration on the way up, it's neither increasing or decreasing. So we've got a neither on that. At the top, it's neither increasing or decreasing. It's just its value. And the acceleration is constant. It's minus 9.81 meters per second squared. Doesn't change until it hits the ground after it's come back down. And so you can say that. Questions like this, though, when you reason your way through them, it's a good idea to do that. And they have, in the back of your textbook, there are conceptual questions. I wasn't able to put a lot of them on the homework, but they're good things to get you thinking about some of these ideas. Okay, here's one where we're actually going to have to plug numbers into it and figure out what we can here. We have a hot air balloonist and probably balloon as well. Oh, the balloonist is the person on the balloon though, I guess. So we have that. Okay, just a second. I've got a sneeze coming on, but maybe I can write down some equations. I'll write down our Freefall equations here that we were using yesterday that are in this part of your formula sheet. I've been using G is 9.81 meters per second squared. Now that's the value of the magnitude of G. We say that the acceleration here is negative G. So little g just stands for the magnitude of that. And if I want to put that on there, I will. So our velocities look like v equals v naught minus gt. Our y value looks like y naught plus v naught t minus 1/2 gt squared. And maybe we can use this other equation, v squared equals v naught squared minus 2g times y minus y naught. So we'll see what we can do with those equations today and see how this will work. Okay, first thing they have you do is compute the position and velocity of the sandbag at 0.250 seconds and 1 second after release. Well, here we're going to need to read the question first, I guess. It says it's rising vertically with a constant velocity of magnitude 5.00 meters per second. And the balloonist releases a sandbag at an instant when the balloon is 40.0 meters above the ground. So if I was to make a sketch of this situation, this will test my drawing abilities for sure. All right, we'd have a bunch of strings going up from this thing. And there's the balloon up there. And so we'll imagine that leaning out of this thing is the balloonist, and he's holding this sandbag here. And at the instant he releases it, it is 40.0 meters above the ground. So that's where the sandbag is at that instant. And the balloon, the balloonist, and the sandbag are headed upward at that instant at 5.00 meters per second. Okay. So something we'll learn about shortly, well, actually after the first test, when we study Newton's laws, is that when the balloonist lets go of that sandbag, it doesn't instantaneously stop and instantly start falling downward. It's going up at 5 meters per second with him. And so the instant he lets go of the sandbag, it is still going upward at 5 meters per second. And so we have to think carefully about that. But as soon as he lets go of the sandbag, we don't care what happens to him or the balloon or her or the balloon. All we care about is the sandbag. So here's what I can write down for that balloon. I can say that where it is at time 0 is going to be those 40.0 meters above the ground. Its initial velocity, v naught, is going to equal, whoops, v naught equals, not a sign, but it's going to equal 5.00 meters per second. I didn't put a plus sign on it, but I know that it's going up, and so I just didn't put a minus sign on it. So those are my initial conditions. The acceleration is minus g, just like we always have. And so I can have y is going to equal y naught plus V naught y, whoops, just V naught. I'm not using an extra subscript yet. V naught t minus 1/2 gt squared. And V is going to equal V naught minus gt. So those are my equations, but I can plug numbers into those in this case. And let's see, 40.0 meters plus 5.00 meters per second times t minus 1/2 times 9.81 meters per second squared times t squared. I'm trying to leave myself room over here for drawing a table, but maybe I'll just do that on an extra piece of paper. And this will equal that initial velocity, 5.00 meters per second minus 9.81 meters per second squared times t. Okay, so those are the formulas that I can use for computing the position and velocity of the sandbag at these two times. Let's see, I'll just flip this around and make a table on here. I want to have this little table that has position and velocity at these two different times. So position is x in meters, and I put both the quantity and the units that it'll have here. And then V is meters per second, and I probably should have had a top row on here that's going to be t in seconds. Okay. And I want to calculate this at 0.250 seconds and 1.00 seconds. So, and what I'll do is I'll just plug this into my calculator here for these various times. And I think what I'm going to do is try to put them in such a way, whoops, turn on the calculator first, always works better. Put it in such a way that I can change the time, just go into the equation and edit it rather than having to plug all this stuff in again, although probably doesn't matter. 40 plus 5 times, the first time is 0.250, and then minus 0.5 for the 1/2 times 9.81 times 0.25 squared So after, let's see, that 0.25 seconds, I got 40.9 meters for X. So not all that much higher. For the velocity at that time, I would just take 5 meters minus 9.81 times 0.25. So and at that time, it's only going 2.55 meters per second. And again, I put the units over here on the left, so everything in that row will have those same units. And that's how I did it. Now I can figure out the height at 1 second. So actually, yeah, I don't know what the best route is. I'll just punch it in again. 5 plus, or 40 plus 5 times 1 plus 0.5 times 1 squared. Okay, I get 49.9, or no. Yeah, position-wise, I get 49.9. Whoops, no, I don't. I made a mistake. I forgot to put a minus sign on that last term. So okay, I get 40.1. Okay, now the fact that this height at 1 second is less than the height that it was at 0.25 seconds tells me that somewhere between here and here, it started to drop. Well, if I look at the velocity here, 2.55 meters per second at this time, it already lost roughly half its speed in just a quarter of a second. So I think it's going to stop soon. In fact, I would expect to have a negative velocity here. And if I do take 5 meters per second minus 9.81 times 1, I will get a negative velocity. So 5 minus 9.81 times 1, but whoops, not 981. And I could do the times 1, but it won't have any effect. Anyway, it's minus 4.8. Okay, so in between 0.25 seconds and 1 second, it stopped in reverse direction, and it's already barely above the initial height that it started at. Now, where's the balloon? The balloon is still going upward at 5 meters per second. So after 1 second, that hand that was reaching out over the basket of the balloon that let go of the sandbag is going to be at 45 meters. So it'll be 4.9 meters above that point right there. And so the balloonist will see that sandbag accelerating away downward at 9.81 meters per second squared, dropping away from it. And it was dropping away from it right from the word go. So, or right from the let go, I guess you could say that. So that's what those things look like. Now, it asks, how many seconds after its release will the bag continue to rise? Well, okay, here's how you can figure that out. Take the velocity equation, v naught minus gt. It stops rising. When it stops rising, the velocity will equal 0. So we did something like this yesterday. Just set this equal to 0 and then solve for the time. And so we would get v naught, kick that across. V naught will equal gt, or the time will equal v naught divided by g. And I know at least once yesterday we used this equation or relation to figure out how long something thrown or launched straight up would rise. And just take our 5 meters per second and divide by 9.81 meters per second squared. And again, g by itself means 9.81 meters per second squared. Here we've got a minus sign on it because its direction is downward, but then you can just do algebra with it, kick the gt across and change its sign. So we get that, and we'll get about half a second here. 0.510 to 3 significant figures. Seconds. And again, meters per second divided by meters per second squared. You divide by a fraction, you flip it and multiply. So this would equal meters per second times seconds squared over meters, and the meters divide out, and seconds squared over seconds are just plain seconds. So that's what we have. So that's the time at which it stops rising. Now, what's the greatest height above the ground the bag reaches? Well, I think it's going to be somewhere between, I don't actually know, but probably a little bit more than 40.9 meters. So let's find out. Now that we know when it's at its highest point, y equals y naught plus v naught yt minus 1/2 gt squared. So I just plug in the numbers. Y naught was 40.0 meters plus v naught y was 5.00 meters per second times 0.510 seconds minus 1/2 times 9.81 meters per second squared times 0.510 seconds squared. I know the units will end up meters because I start with those here, meters. Meters per second times seconds is meters. Meters per second squared times seconds squared is also meters. So y will end up being, this is plug and chug on the calculator, 40 plus 5 times 0.510 times 0.5 times 9.81 whoops, hit a wrong button there. I wanted a minus sign there. No surprise. 9.81 times 0.510 squared. And I get about 41.3 meters. So it doesn't go much higher than it was when it was released before it stops. So, okay, there's one more part to that question. Actually, there should be two more parts. This is part E. I don't know where part D went, if there was a part D. But it says sketch A versus T, V versus T, and Y versus T graphs. Well, that's kind of interesting, but I think I can do that. Let's see. I think if I make them lined up vertically above each other, I can have the same time scale for each of these. So I'll just sort of make 3 graphs here. V versus T and Y versus T, So the first graph is A, and its units are meters per second squared. And when you make a graph, that's something you do, is put the units on the thing. And this one's kind of boring because here's what it looks like. Minus 9.81, and again, the units are meters per second squared because I labeled that up there. The acceleration is constant. As soon as the balloonist lets go of the balloon, it's in free fall, and it has an acceleration of 9.81 meters per second squared down, which is negative. So that's what the acceleration looks like the whole time. Pretty dull. However, V versus T is a little bit more interesting. So let's see, for it, V in meters per second, I'm going to make the, oh, by the way, this is the T axis, T in seconds. This is also the T in seconds axis for that one because it's V versus T. And V starts off at 5.00 meters per second, but it goes negative shortly after that, or drops to 0. And we figured that out somewhere here, wherever I wrote it. it stops rising at 0.510 seconds. And so I wonder if D might have been to ask how long it takes to hit the ground. I don't know. Anyway, 0.510 is when the velocity of the thing goes negative, and then it just gets more and more negative on the way down. And so that's what we're going to have in that chase. Now, the Y versus T graph, I'm not going to be able to put quite as much accuracy into it, but can make another sketch for it. This is Y. Oh, that's not where I wanted to stick that thing. I wanted to have the horizontal axis be more like down here. Okay, so ignore that line. Pretend you never saw it. T in seconds, again, is the horizontal axis. Y in meters. And actually, I may let this number right here represent 40.0 meters, or this little tick mark here. Now, that's where the balloon is at 0.510. The balloon has risen to 41.3 meters. And so if I extended this over here, it's 41.3 meters. And it was rising for that time. And then it'll start to fall. And after another 0.510 seconds, it's actually going to be 0.510 plus 0.510 is 1.02. Or no. Yeah, I think it's 1.02. Yep. So this is 1.02 seconds. What happens at that time is that it's come back to the height from which it was released. Okay. And so it does that. But then it's accelerating downward, and so its slope gets steeper and steeper until eventually it hits the ground. Now, I don't have this drawn very accurately. If this is 40 meters, this height is too big to be only 41.3. So not such a great drawing, but at any rate, that's a sketch of sorts. Not a good one, but you can see the A versus T graph is the simplest one for an object in free fall. It's constant. It's always minus 9.81 meters per second squared. V versus T for something that's thrown upward is a nice straight line when you have constant acceleration, and the Y versus T graph is actually a parabola. So that's what that thing looks like. So we kind of nailed just about everything, and I think that was all for the examples I had of projectile motion. But I do want to show you one, and maybe I'll pick one of yesterday's examples. Yeah, we'll do a rock dropped from a height 75.0 meters above the ground. Back, phone's ringing. There. Usually when my wife's home, I have that door shut all the time, but she's out of town. So anyway, a rock is dropped from 75.0 meters above the ground. Let's see. Let Y be positive downwards. Ran out of room. And what else do I want to do? Find when the rock hits the ground, and B, the velocity of the rock when it hits the ground. Okay, so I'll draw a new picture for this situation, and we could imagine that this is just a bridge that's going across the Crooked River in Central Oregon. But anyway, we've got this person up here holding a rock out over the thing, and they let go of it, and we'll just imagine that this distance is 75.0 meters from where it's first let go. Now what I'm going to do is I'm going to define, this is where y is equal to 0, where it's originally released from, and I'll call that y naught because that's where it's released from at time 0. And then this is where y is going to equal 75.0 meters. And so positive is downward here. Okay. Now the effect that's going to have on my equations is that those equations where I usually had y equals y naught plus v naught yt minus 1/2 gt squared, it's going to change that minus 1/2 gt squared into positive 1/2 gt squared. And the v equation ends up looking like v naught plus gt. So if I choose down to be the positive direction, the acceleration is now a positive acceleration. And so it'll look like that. So it says the rock is dropped. Okay. What that means is that V naught is 0. It's not thrown, it's dropped. And so V naught is 0. And also from my picture here, I'm going to let y naught equal 0 as well. And so y naught is 0. And so first question is, I'm supposed to figure out when the rock hits the ground. Well, here's what happens to the y equation. Y is going to be 75.0 meters when it hits the ground. And that means 75.0 meters will equal y naught, but y naught is 0. So that part's not there. Plus v naught t, but v naught is 0, it's dropped. So both of these terms disappear and I just get 1/2 gt squared. 75 meters is equal to that. This is handy. The distance that a dropped object falls is, if you just let go of it, if you drop it, it's just going to be 1/2 gt squared. And that's where it's going to be at some particular time. So I just need to solve this for t. And when I do that, let's see, multiply both sides by 2, and I'll get 2 times 75.0 meters equals gt squared. Remember, g is 9.81 meters per second squared. Or I would get t squared is equal to 2 times 75.0 meters divided by g, but now I'm going to write that in as 9.81 meters per second squared, or t t will equal the square root of all that stuff. 2 times 75.0 meters divided by 9.81 meters per second squared. And I'm just going to plug it into my calculator that way. Unit-wise, if I'm dividing meters by meters per second squared, flip the fraction and multiply, and I'll get meters times seconds squared per meter. I'll get seconds squared, but that's under a square root. So when I take the square root, I get seconds. And I'll just do this. I'll hit the second square root, and then 2 times 75. And I could put 0.0, but my calculator doesn't care. I know enough to round my result to 3 significant figures. Divided by 9.81. And I get the same answer we got yesterday, 3.91 seconds. So that's when the rock hits the ground. And then the velocity of the rock when it hits the ground, well, V is V naught plus GT, but V naught is 0, so that's gone, and it's just going to equal 9.81 meters per second squared times 3.91 seconds. So multiply that by 9.81. Then I get 38.4 meters per second for that one. Okay, actually, there is one more problem I could do. Actually, I'll print it off and talk about it, and we can try it as our first thing tomorrow, or I'll show it to you anyway, if I can remember where in the world I put it. Let's see. I thought I just opened that. Here we go. Here comes a jet. Oh, nope, that's not a jet. Maybe they're cleaning the streets outside. So this may get noisy here. We'll see. Sorry that you can't see this right now. I just need to change a page layout. We can look at it. Okay, this is one that I often have on the very first homework in engineering physics. And that class goes a little faster than this one. But here's the situation. A flower pot falls off a windowsill and falls past the window below, and you can ignore air resistance. It takes 0.420 seconds to pass this window, which is 1.90 high. And how far is the top of the window below the windowsill from which the pot fell? This is kind of tricky. So let me draw a picture to illustrate this thing. And we'll start with this problem tomorrow. And then tomorrow we're going to be starting projectile motion. So you may read a little bit farther in the book to start getting some ideas about that. But here's the idea. We've got some kind of a multi-story building here. And there was a window up here and a window down below, and somehow this flower pot gets knocked off that windowsill up there. Maybe they had a cat or something. Anyway, and there's your flower and stuff. Anyway, it's sailing down here, and this window here, which is 1.90 meters high, or from top to bottom, that's what it is. The flower pot takes 0.420 seconds to sail past that thing. And so knowing that information, we want to figure out what height the flower pot fell from. And so, this could be a little bit of a challenge. So think about that, and we'll start off with that problem tomorrow. Okay, any questions that popped up on these things? I hope I'm doing enough examples where you'll get a feel for this. Try working these on your own, or looking in the book and finding some other ones. I think the odd numbered problems in the book have the answers in the back, so you can do more of them for practice, and then check out the online homework too. So, all right. Okay, I'll try to get this posted sooner today. I keep getting going on projects and forgetting to post this as soon as I ought to, but after I press stop here, it has to get processed on my computer first, and then I have to upload it to YouTube, and both of those processes take a while, but I'll try to not eat lunch in the meantime and forget about what I was doing. So, all right, I'll see you tomorrow.